Welcome back to Chemistry Matters and Unit 5, Chemical Reactions. In our last video, we learned about different types of chemical reactions. Just because you mix chemicals together doesn't mean they're going to react. In some cases, energy has to be added, like in a combustion reaction. And in other cases, reactions simply don't occur at all. Now we're going to figure out trends that help predict which substances will react with each other and which ones won't. So let's head out to our classroom and see what some of our students are doing to figure this out.
We've been studying chemical reactions, but I'm sure you've noticed that just because two chemicals touch, that doesn't mean that they'll always react with each other. So in this lab, what we're going to do is we're going to determine a pattern of what does and what doesn't react. And we'll do this by using several different metals along with their metal nitrate solutions. So your task is to mix each metal with each solution and make observations about which combinations react. Now be sure you plan an organized way to collect your data and make sure that you're always wearing your goggles, gloves, and aprons at all times. Let me know if you have any questions.
Okay, we have all these different metals and all these metal nitrate solutions, and we need to see what will react. So what should we do first?
Can't we just mix them all together and see what happens?
We should mix everything, but if we do it all at the same time, we won't know what's reacting with what.
Good point. I'll make a data table. Would you list off all the metals and I'll put them in the first column?
Okay, magnesium, copper, lead, and zinc.
Now I'll write the solutions across the top. What are they?
Magnesium nitrate, copper 2 nitrate, lead 2 nitrate, zinc nitrate, and silver nitrate.
We have silver nitrate, but no silver. For all the other solutions, we have the metals too. I wonder why we don't have any silver.
Well, that's a good question. And as you can probably imagine, silver is very expensive. But for this lab, the silver nitrate solution will work just fine.
All right, now we can start mixing things together.
Let's split up. I'll take magnesium.
All right, I'll take copper.
I'll take lead and you have zinc.
So be sure you're placing the correct solution in the right wells. You all made data charts showing the results of the chemical reactions that you just performed. So let's examine those results. What trends did you observe?
Well, it looked like the magnesium reacted with every solution.
Copper didn't react with anything but the silver solution, so we're not sure if we might have done something wrong.
For us, lead only reacted with the copper and silver solutions.
The zinc reacted with everything except for the magnesium solution.
So if you had a sample of silver, what do you think it would have reacted with?
Since it looks like the silver solution reacted with everything, I think the silver metal would too.
But the magnesium metal reacted with everything, while the magnesium nitrate solution didn't. I think the silver metal wouldn't have reacted with anything since the silver solution reacted with everything.
I don't think the silver would have reacted either.
That makes sense to me. I mean, I wear a silver bracelet and I've never seen it react with anything.
Those are some great points. So take your data and list the metals with the most reactive at the top.
That'd be magnesium, zinc, lead, copper, and then silver.
This is a simple activity series, which is a list of metals or nonmetals in order of decreased reactivity. Chemists use this data to predict whether reactions will occur between metals and metal ions. There are other activity series with halogens and their ions. Use this activity series here and tell me what would be produced when copper metal reacts with magnesium sulfate.
Well, since the magnesium solution didn't react before with copper, I don't think it'll react here either, because it's still a magnesium ion.
Wait, does the sulfate instead of nitrate make a difference?
I think it's just about the metals and their ions. The magnesium metal reacted with a lot of stuff, but the ion didn't.
I think you're right, but you're not using the activity series. Copper is lower on the series than magnesium. I think this is how we can use the list.
So if a piece of copper was combined with silver sulfate, it'd react, right? Silver is below copper on the list.
And this is exactly how you use an activity series. And here's a more complete activity series. And you can see that it has metals and halogens on it. Now, this is only used to predict certain types of reactions. So what kinds of reactions have we been dealing with today?
Since there were metals by themselves and ionic solutions, these are single displacement reactions.
Yes, and that's what you see here. To use an example, you showed us that copper metal would react with silver sulfate, which matches the definition of a single displacement reaction. And we only use activity series to predict single displacement reactions. Reactivity explains why some things like gold jewelry don't react. And now you know how to predict the products of a single displacement reaction using an activity series. But we've also examined 4 other types of reactions. And so you already know how to predict the products of combustion reactions.
Sure, they always produce carbon dioxide and water.
So what about synthesis reactions?
Well, you can figure this out. Look at this equation. How can you predict the products of a synthesis reaction? What are the reactants of a synthesis reaction?
I think I know the answer. You have to know the reactants to predict the products in a synthesis reaction. Synthesis reactants are things alone or by themselves.
Well, what do you mean?
I think she means that the reactants in a synthesis reaction aren't bonded. They're by themselves, or diatomic molecules like oxygen.
Like with the burning magnesium. The magnesium is by itself and it reacted with the oxygen gas, which is a diatomic molecule.
Great example. So how do you know what the product is going to be?
Don't you just mush them together?
How do you know they mush? Well, actually, bond is a better word. How do you know that they bond together?
Well, just combine them, MgO2.
Doesn't magnesium make ionic compounds? Don't we need to think about the charges?
And remember from Unit 4, when it's an ionic compound, we definitely need to think about the charges.
So the product would be MgO because that's the neutral formula?
That's correct. Now, someone summarize how to predict the products of a synthesis reaction.
You put together the 2 reactants, and if they're ionic, make the formula neutral. But what if it's not ionic?
Well, covalent molecules can form from a synthesis reaction too, but they're a lot more difficult to predict. And so we're not going to predict those in this class. Now, since decomposition reactions are essentially the opposite of synthesis reactions, how do you think we can predict those?
Just take them apart.
Well, essentially, yes, but you have to watch out for diatomic molecules. Do you remember when we decomposed the water? What were the products?
Hydrogen and oxygen.
Both of those are diatomic, so wouldn't it be H2 and O2?
That's right.
Is it really that easy?
Yes, but there are some more complex decomposition reactions. When metal carbonates decompose, they form metal oxides and carbon dioxides. So what would sodium carbonate form when it decomposes?
That doesn't seem too hard. Sodium oxide and carbon dioxide.
Exactly. So I want you to see if you can figure out how to predict double displacement products on your own in a lab. On your lab table, you have solutions of sodium chloride, NaCl, potassium iodide, Ki, and lead 2 nitrate, PbNO3 You also have a solubility table, which displays the ability of a substance to dissolve or dissociate in water or acid. So develop a plan and collect data that will help you predict when a double displacement reaction will occur. Go ahead and get started.
First, let's make a data table so we can stay organized.
We'll need to be really specific about the names and amounts of each chemical reactant.
Start with the first solution, sodium chloride, and mix it with the other 2 solutions in separate wells of our spot plate.
Nothing seems to be happening for some of these.
The lead always reacted.
Well, how does your data relate to the solubility table?
What do we look for on the solubility table?
Well, I looked up all the solutions we're using, and they're all soluble.
That's because they're solutions. Did you look at the products?
How do I know what products to look up?
Good point. We have to figure out the products. These are double displacement reactions, so we should switch the cation ions, right? I mean, write the product so that each cation ion is with another anion.
When you're done, use the whiteboard to write out your equations.
Okay, so potassium nitrate is soluble. And lead-2 iodide isn't. So is that what the yellow stuff was? The lead-2 iodide?
I believe so. Let's look up the products of one of the mixtures that didn't react. Sodium chloride and the potassium iodide did not react.
Sodium chloride and potassium iodide both are soluble in water. So all 4 ions are dissolved in the water.
So the lead-2 iodide is the precipitate, and the potassium stayed dissolved in water.
Good. And as you recall, another word for dissolved in water is aqueous. So what did the rest of you think of Josh's analysis?
That makes sense to me. Look at our equation. When we saw a chemical change, one of the products wasn't soluble.
And when nothing happened, everything was soluble in the water.
And what did your team find?
Well, we found that when the sodium chloride and the potassium iodide were mixed together, there was no reaction.
Yeah, the ions must have been floating around in the water.
Nice summary of your observations.
Before we continue, it'll help to learn how to draw particle models of chemical reactions. These are similar to simple animations, using circles of different colors to represent atoms. You'll show the atoms before the reaction, the reactants, and after the reaction, the products. This is a simple example, a particle model of the reaction between copper and silver nitrate. Copper and 2 silver nitrate yield 2 silver and copper nitrate. To represent the reactants, this orange circle represents the copper atom. These are 2 silver nitrate molecules, each with 1 silver atom in gray, 1 nitrogen atom in blue, and 3 oxygen atoms in red. The product is the orange copper atom, now with 2 nitrates, 1 on each side. Each nitrate is made of 1 blue nitrogen circle and 3 red oxygen circles. The other product is 2 silver atoms by themselves. The great thing about a particle model is that it makes it really easy to count the atoms in the reaction to make sure all the numbers of atoms match before and after the reaction. So with that in mind, let's head back out to our classroom to see how our students do with this.
With a partner, draw a particle model on your whiteboard of the potassium iodide and lead-2 nitrate solutions before the reaction. Be sure your model represents the different ions in each compound in the solution. And on another board, draw a particle model after the reaction. So how do your models represent what was happening in the reaction?
Well, we drew lead-2 iodide together.
That's good, but why didn't you put the potassium and the nitrate on your model?
Because we can't see them in our reaction.
Okay, you're right. You don't see evidence of them, but they're still there, right? I mean, how do you know that?
I guess we know that they're still there because you have to start and end with the same amount of matter.
Oh yeah, I think that's the law of conservation of matter, right? There's nowhere else they could have gone.
You're right. How about you guys? Did you include the lead-2 iodide?
Yes, after the reaction, we drew the lead-2 iodide all together on the bottom of the container.
Good. How about the potassium and the nitrate?
We drew them separate from each other since they're soluble and dissolved. We also showed that potassium is a positive ion and nitrate is a negative ion.
Good. Well, how is that different than the lead-2 iodide?
Well, the lead-2 iodide isn't soluble and looked thicker, so we drew that together at the bottom.
Great. Well, how would a particle model look different if, let's say, we had sodium chloride and potassium iodide mixed together?
All the ions would still be there, but they'd be dissolved in the solution.
So nothing would change from the reactants to the products, so no reaction would occur.
You're right. And a change has to occur for it to be considered a chemical reaction. And we can use the information that you guys obtained from lab, as well as the models that you created to determine which parts actually changed. And this is called a net ionic equation. And it's an equation that just shows the ions or the substances that are involved in the chemical reaction. And as an example, we have the reaction between potassium iodide and lead-2 nitrate. And the lead and the iodide ions were the only ones that were actually reacting, so that's why this is called a net ionic equation.
Our students were on a roll there. If you need additional help with net ionic equations, take a closer look at our net ionic equations video. But before you do, let's review the key concepts of this unit. We've investigated the law of conservation of mass. We practiced balancing and identifying types of reactions. And we've learned about how to predict the products of reactions. That's a lot, but it shows us how chemical reactions surround us in our everyday lives and why they're so important. Join us in the next video on the Unit 5 playlist to see how we can use this new knowledge to identify unknown substances. I'll see you there.